Good afternoon, everybody. I'm going to introduce you to probably the most coolest thing you've ever seen to do is the Taylor series. So I'm going to find what's e to the I pi plus 1 using Taylor series. Well, you know that I was imaginary number, and both pi and e were non-repeating decimals that probably would never find, you never put into a real number. But I'm telling you right now that somehow, miraculously, e to the I pi plus 1 equals to 0. Wait, what? Yeah, you heard it correctly. This weird number actually goes to 0. Now, I'm going to prove that using Taylor series. First, I'm going to say that I to the pi equals to x. And x is just some number that I imagined out. And since e to the x is equals to 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x to the third plus 1 over 4 factorial x to the fourth, and this keeps going. I'm going to substitute I pi as x into this whole equation. So you have I plus I pi plus 1 over 2 factorial I to the pi square plus 1 over 3 factorial I to the pi to the third plus 1 over 4 factorial I to the pi to the fourth, and this keeps going. Now you're wondering, how could this be similar, and this doesn't look simpler at all. But wait, I'm going to regroup this whole thing into two groups. First, I'm going to say that the Taylor series end up in 1 over 2 factorials. I'm going to regroup as 1 plus 1 half I over pi square plus 1 over 4 I over pi to the fourth. Notice I'm doing all the even factorials in one group and then putting all the odd factorials in another group. I say this is group 1 and this group continues. And since this is all plus, the second group should be plus I pi plus 1 over 3 factorial I over pi to the third plus 1 over 5 factorial I over pi to the fifth. And this keeps going too. So how does this change everything? Well, there's something really tricky about I. Let's just do some basic calculations. Let's say we know that I is the square root of -1. So what do we know about I squared? I squared is -1, square root of -1 square, which is -1. And what's I to the third? Well, since I to the cube is -1, so I to the third will be -1 times square root of -1 is negative square root of -1. And I to the fourth will be simply I to the square is 1. I to the fifth is I to the fourth times I equals square root of -1. Notice there's a really good pattern here. You have -1, square root of -1, -1, negative square root of -1, 1, and square root of -1. This thing is going to play the major role of proving that e to the x, e to the I pi plus 1 equals 0. So in this case, I pi to the square will be equal to I square pi square, and we know I square is -1. We know that I pi to the fourth is I to the fourth pi to the fourth, and I to the fourth we know is 1. And in here we know I pi to the cube is equals to I to the cube pi to the cube, and in this case I to the cube will be negative square root of -1. Well, if it is negative square root, I'll write it as negative I, so it looks a little bit better. That's the one reason that we use I instead of square root of -1. So I'm just write this whole equation above into this 1 minus 1 factorial pi square plus 1 over 4 factorial pi to the 4th minus 1 over 6 factorial pi to the 6th. This keeps going on. And plus I to the pi minus 1/3 factorial I pi cube plus 1 over 5 factorial I pi to the 5th minus 1 over 7 factorial I pi to the 7th, and this keeps going too. And how do I get this is negative in front of 1 over 7? If you keep going doing this oscillation of I from I to the 5th, you'll have something like plus and minus, plus and minus, plus and minus. Does anybody recognize this thing? The both of these two groups looks a lot like sine of x. And this thing looks a lot like cosine of x. How do I get that? Because first of all, if I take an I for the second group, you have an I is pi minus 1/3 factorial pi cube plus 1/5 factorial Sorry, that was a mistake. So in this case, this thing will look a lot like cosine pi, because cosine pi is 1 minus 1 to factorial pi to the square plus 1/4 factorial pi to the 4th, and this goes on. So this whole chunk just became cosine of pi, because the Taylor series for cosine of pi is exactly what it shows over here. And here, for the second group, notice that there was an I in front of every single term. So I just take out the I in front, and this whole thing, what it looks like, pi plus minus 1 over 3 factorial pi to the cube plus 1 over 5 factorial pi to the 5th minus 1 over 7 factorial pi to the 7. This second group somehow miraculously looks like sine of pi, because the Taylor series of sine of pi is the exact same thing as the one showed up in the second group. So I can rewrite the whole thing into cosine of pi plus I sine of pi. This thing is just what we deducted from e to the I pi. And since cosine of pi is -1 and sine of pi is 0, so you have -1 plus I times 0. And for zero property, no matter if this is a real number, imaginary number, or any number times 0 will be equals to 0. So this whole thing becomes -1. So e to the I pi equals -1. What we're trying to find? E to the I pi plus 1. So in this case, it will be -1 plus 1 equals 0. Pretty cool, right?